All right, good morning, or sorry, good afternoon, everyone. It's Friday, right? So just a quick note on something from the last lecture. So if you remember, we have these two different ways of tuning lasso plus least squares. So you use lasso to figure out which coefficients to select, and then you use the least squares to fit the coefficients. And there's this pipeline approach. And then there was also a different approach which used a for loop. And one thing that was a little bit counterintuitive was that the performance with the for loop approach was slightly better than the performance here with this pipeline approach. But then I had the idea, well, maybe if we use the one standard error rule, it might work better. And so in the one standard error rule, what you do, if you remember, is you first figure out what is the value of the whatever you're tuning, in this case alpha. You find the value that minimizes the mean squared error, RSS, which is this value here. And then you set your target as that plus one standard error. So that's our target. And then you look for the simplest model that falls under the target. And simpler here means larger alpha, because larger weight, fewer coefficients. So that would be this. So this would actually be the one standard error alpha instead of this one. And when you do that, you actually find that you select exactly the same features as in this model. You get the same performance. And so I thought that was kind of nice that it worked out that way. So I updated the demo. I updated the lecture slides. So now these two methods tie. Actually, these three methods all tie for that demo. Okay, so today we're going to talk about a super important concept called maximum likelihood, which is going to pretty much be the way that we approach machine learning from now on in the course. This is very important, and it involves putting together a number of the tools that we've learned until now. And essentially, it frames the entire maximum machine learning design problem as estimating statistical parameters in a probabilistic model of the data. Okay, so what do we mean by that? So we'll kind of go through this slowly. We'll come out of this with two different procedures. One is going to be called maximum likelihood. The other is going to be called maximum a posteriori, or MAP. So let's just start at the beginning. Let's remember that if we have a random variable like y, usually it depends on some parameters that govern that random variable, right? So for example, if we're talking about a Gaussian, we have the mean of the distribution, we have the standard deviation sigma, or equivalently the variance sigma squared. And if you tell me those two things and that it's Gaussian, then I know exactly what the distribution is, because those are the only two parameters that affect a Gaussian, right? So we can think of this. Okay, we have a random variable. In this case, it's Gaussian with these two parameters. And so hopefully that's a pretty familiar concept. We have this bell curve and so on. And what we find ourselves doing in machine learning is often we have some probabilistic model similar to the one on the previous page that depends on some parameters theta. So for example, maybe that model is Gaussian, in which case we would have two parameters in theta, mu and sigma squared, or mu and sigma. Okay, but there may be other parameters in the models we encounter. But importantly, we have a bunch of data which we use to fit or estimate those parameters. That's the main thing that we have in machine learning, is a bunch of data. So that's going to be our objective, is to figure out how do we adjust the parameters theta in this statistical model to best match the samples or the data that we've acquired. Okay, so it goes like this. You think of this quantity. This is called the likelihood function. This is basically very similar to this one over here. Here, it was written in terms of one single y. Over here, It's written in terms of all the data that we've collected. Okay. The important thing is, when we think about this function in this context, what is the variable that we're adjusting? What's like the so-called independent variable here? Theta, right? Y is fixed. Y is our data. That's very different from when you usually see pictures like this. In your mind, you're actually thinking of this as a function of y for fixed theta. That's not what we want to do anymore. We want to reverse it. We want to think of theta for fixed y. And when we do that, we give it a different name. For a fixed y, this function versus theta is called the likelihood function. Okay. Whereas if we come back over here, we might say, well, this function is the PDF of y. Because then we're thinking about y being many different possibilities. Here, y is fixed. That's our data. We're thinking of theta as being many possibilities. We want to find the theta that best matches that y. Yes?
Is there a particular reason why we want to think of y as fixed? Again,
yes, because we've collected that data.
Oh, great.
So that's why it's fixed. The data has been collected. That's what we have to work with. We know what that is. What we don't know is what theta is. Okay, so that's the thing that we're going to use. And at the end of the day, what we're going to do, this is called maximum likelihood estimation, is we're simply going to maximize that versus theta. Find the thetas that maximize that. So it's like you're finding the parameters such that the data you collected is the most likely fit. Okay. So this is maximum likelihood. That's the idea. That's the definition. So the question is, okay, how exactly do we do that? So let's go back 1 second, talk about the rest of this. So the most common assumption, the one we're going to use all semester, is that these different samples here are independent and identically distributed if you fix everything else in the problem. So in this case, if we fix theta, so on, we're going to think of these as IID. In that case, so this quantity here, this is what you would call, from one perspective, you could say this is the joint PDF of some vector of values theta for some parameters, vector of values y for some parameters theta. But if you think about that as the joint PDF, and you think of these as random variables that are independent of each other, then we know statistical independence means you can just decouple that joint into a product of individual PDFs like this. Okay, so if we say, or if we think of our samples as independent random, given theta, then we can simplify this to a product of marginal or scalar PDFs. Does that make sense? That's what we're always going to do. We're always going to think about each of these samples I've collected. This is just over the n samples of my training data set. They're all coming from the same model, exactly, and they're all just independent samples of that model. Okay, and what this is going to do for us is this is going to make the derivations a lot easier. If you can't make this, it could be pretty messy. But we're going to make this, and that's assumption, and then the derivations will be a lot easier. Okay, so what we're going to do as we go through this chapter and the next one and the next one and so on is we're going to be basically coming up with different models for this likelihood. And then for whatever model we're working with, we will just come up with a way of optimizing this over the parameters theta, and that is essentially machine learning. Building a model, a probabilistic model, doing some sort of optimization over your parameters, and then once you have that model, you can use it for prediction. And so maximum likelihood is the framework that we're going to use, and today we'll see that this is the way to explain the RSS stuff we have been doing. We'll actually understand that that's just a specific case of this. So we've kind of been working our way up to this. This is really putting everything together for the first time. Okay, any questions so far on the high level? So we're going to come up with a probabilistic model. We're going to plug in our data y. We're going to have some unknown model parameters theta, and we're going to do some sort of optimization to figure out which theta maximize that likelihood. And we're going to call this maximum likelihood. Okay, so now when you actually start to do this practice, whether it's a homework or whatever, you may have noticed that a lot of the probability distributions that you see have exponentials in them. Like Gaussian is like exponential of a quadratic, right? And Laplacian is exponential of absolute value. Then there's the exponential distribution. There's so many distributions that have an exponential in it. And for that reason, it's very convenient to take the log of this likelihood rather than the likelihood itself. And it turns out because the log as a function is strictly increasing, if you find the theta that maximizes the log of this function, you're finding the same theta that maximizes the original function. So you can put in the log there, and it does not change the location of the maximum. You could say that it's order preserving the log because it doesn't, if there was a certain theta that was your maximum, and now you look at the log of the function, that theta is still going to be your maximum. It's not like some other theta will all of a sudden surpass it, and they will change ranks. It's like the theta that originally was the maximum, or the maximizer, is now going to be the new maximizer. So by putting in that log, we make our lives a lot easier in terms of the derivations that we have to do for this maximum likelihood problem. Okay. So we're going to look at the log. And then the second thing people often do is people like to work with minimization problems for some reason more than maximization problems. And so instead of maximizing the log likelihood, you just minimize the negative log likelihood. So now you've turned it into minimizing something. It's just a notational convention. Okay, so this is the final expression. Let me erase this. So typically, from just a definition point of view, this makes the most sense. But then from an actual computation point of view, this is what you do. You minimize the negative log likelihood. Okay, is everybody with me so far? Okay, so we just have to figure out a few details and understand this a little bit better. So one important point about this is that when you're doing this fit, you are using no prior beliefs about your parameters theta. Maybe you know something about theta, but in any case, you're not using it when you do this. The theta here is just, all you're using is this function, the likelihood, which connects theta to your measurements. The actual values of theta, you're not assuming anything about. That can be good, or maybe it's not good. Maybe you actually want to bring in some prior knowledge. So when we want to bring in that prior knowledge, we'll turn to the map framework. So let's just work with this maximum likelihood framework for now. Okay, so let's do a little illustration to see just visually what's going on. So we're going to assume that we have a single random variable capital Y, which let's say we know the variance is 1. It's Gaussian. What we don't know is the mean mu. So there's just one single parameter that we're trying to fit. And what we have observed are two samples of that random variable Y. Let's call them y, little y1, little y2. So those are our two data points. This is the model. This is just Gaussian with mean mu and variance 1. Usually the variance would be multiplying this 2, but as you see, it's just 2 times nothing, so or 2 times 1, so that's the variance 1. This is our Gaussian PDF. So this is, if I if I think about it this way, so here I have, when I want to form the likelihood, I have to say what is the probability of receiving those two samples, two measurements, y1 and y2, for a given hypothesis mu. So again, we assume that those two samples for that given mu are independent. So we can write this as the product of this original function evaluated first at y equals 1, later at y equals 2. And more than that, we can actually plug this in, and we get this. So this is our likelihood exactly, and it's going to be a product, in this case, of two things, just two scalar numbers. So here's an illustration. Imagine that this is the y-axis. Imagine that these two values, y1 and y2, are what I have observed. So my goal is to figure out the mu that best explains those two values. So let's just start by saying, well, what if I hypothesize that mu is -1? What would the likelihood actually be? Okay, so this is this PDF here when mu is -1, and this is just plotted for all possible y. To really turn this into a likelihood, we have to plug in the two y that we've observed, which are these two black values. So now we're actually talking about multiplying two numbers, which are these red dots, those heights. Okay, so whatever height the top one is and the bottom one, if you multiply those two heights together, that is the likelihood evaluated at mu is -1. As you can see, that product is not very large. You can definitely make it bigger. What if I instead hypothesize that mu is 1? Then we have the blue curve. Now you can see we get these two likelihood values. I take their product, and that would be my overall likelihood. As you can see, the product of the blue values is going to be higher than the product of the red values. So that means that mu equals 1 is more likely than mu equals -1. But it's still not as likely as we could make things. Essentially what we're doing is we're shifting around that Gaussian bell curve until the two samples located at these two y's, the product of them is as large as possible. So as you can see, as you slide around that bell curve, the way to make the product of those two samples as large as possible is to put it at mu equals 0.2, which is where the green is. And now those two values are up there, and that's as large as it can be, right? Because if I move it to the right a little bit or to the left a little bit, one of those values is going to go down, and the overall product will go down, and it will be less likely. So the most likely point is mu equals 0.2.
Did we switch back to maximizing from, you said minimizing was what we normally did, or did I just miss that?
It's all the same, right? So we maximize the likelihood or minimize the negative log likelihood.
Okay, we were just doing likelihood on that slide.
So yeah, so here we were actually plotting the likelihood itself. And so yeah, we were in the framework of maximizing. And we didn't get rid of the exponential and all that, right? But you'll see in some future slides that we will, to get tractable expressions, we'll take the log, and then they'll turn this product into a sum, get rid of this. It will get a lot nicer.
So the theta is here, but like earlier we basically, so.
Yeah, so here we have a single parameter to optimize, which makes it nice to visualize. Imagine that I was jointly optimizing over mu and sigma squared. So now I would have to make a plane, and I'd have to move that pair of points around the plane and look for, it becomes harder to make the drawing, but it's the same idea. Rather than moving along one axis and finding the best value along one axis, you do it jointly in these two axes, and you look for the maximizing pair. And in general, we work with like a lot of parameters. Once we get to neural networks, we work with millions of parameters sometimes. So there's a lot of things to optimize, but the idea remains the same. Okay, so this is just kind of the visualization of what's actually going on. It's like you're sliding around the model PDF until the data is sitting at the peak. Yes?
Yes, since is across the model, so why don't we just calculate the mu, like if here is the mu equals the mean of the data?
Yeah, you're right. In this case, we can calculate it in closed form, and we'll do so in a couple slides. Most problems in machine learning are not as convenient, and so we don't have a way to just write down the optimal parameters. We will usually have to use an optimization algorithm to somehow learn those parameters, maybe by climbing down a cost function until we get to the bottom. Yeah, but yeah, that's a great point, and we'll actually do the derivation in just a moment. Okay. Yes.
So how does the green curve maximize the probability?
So again, it's all about whatever curve it is. You always need to sample the curve at these locations, which are our data values. So for the green curve, we get these two samples, and then at the end, we just multiply those samples together to get the likelihood. So you can see, like with the red curve, I'm multiplying those samples, pretty small. Blue curve, I'm multiplying those two samples, which is bigger, but not as big as it could be. The largest, shift of this bell curve, which makes those two samples largest, is right here at 0.2, the green one. Okay. All right, so is this kind of making sense? Enough to move on? Okay. So let's do it a little bit more practically. Let's revisit our linear regression problem. Our parameters in this case is all of our betas. Let's write these betas. Let's assume we've standardized our data, in which case we know that the beta 0 equals 0, in which case we can leave it out of our model since we know what it's going to be. And so all the parameters that remain are beta 1 through beta d. We put them together in this column vector beta. And we know from the last lecture, I think we saw this, we can write our model in a vector matrix form this way. So as you go down this y vector, you have your samples I starting from 1 going down to n. And then here are all your training features, training labels. These are your model parameters. And here is the noise that we are adding to our model to make this inequality. I think sometimes we write this with an approximation, but now we're going to be explicit. We're going to say, actually, y is exactly equal to this plus some noise. And furthermore, we are going to assume that these noise terms, epsilon I, are independent of each other, identically distributed. They're all going to be Gaussian with zero mean sigma squared variance. Okay, so let's just assume that, and that, let's see where that goes. So if you think about this a slightly different way, let's say I look at y minus x beta, and I call that epsilon. These are all, vectors or matrices. So I know how epsilon is distributed, right? Actually, no. Let me back up. I don't want to do it this way. So my goal is to figure out, how do I write this likelihood? How do I translate this equation into a likelihood? So the main thing to realize is, beta is going to be deterministic. It's just some fixed numbers we're trying to adjust. X, these are samples we've collected. So these we're going to just treat as numbers we're plugging in. So that's deterministic. The only thing random here are the epsilons. And so if we think about, let's say that this is just some fixed number, fixed vector x beta, and then I'm adding some zero mean Gaussian noise to it, then that tells me that y are going to be Gaussian with this mean. And let's say I look at each of the individual y's. So I look at the first y. That will be the first row of x times beta. That's a scalar, just a deterministic scalar, plus the first epsilon, which I know has this form. So that means that y is Gaussian, variance sigma squared, with a mean given by the first row of x times beta. Does that make sense? So this is supplying the mean, this is supplying the variation, the randomness, and that is our explanation for y. That's just our model for y. So that gives us this model here. Here we're writing it in kind of fancy way. So remember that, let's see. I don't know, have we seen this expression before as a way of writing? I don't know if I'm skipping too many steps here. But basically, here's another way we can think about this. If this is looking unfamiliar to you, that norm is the sum from I equals 1 to n of yi minus xi transpose that vector times beta squared. That's what this norm, squared norm is. So if you have a product, if I have a product of exponentials over I, let me see. We can write this as, let me be more explicit, product of exponentials, and I'll just put in, let's say, f of I. This is exponential of the sum of f of I, right? So it's like e to the a times e to the b is e to the a plus b. So I'm using, this is a case for two variables. If I have many of these, like, n of these multiplications, then I have e to the sum of n things up here. So that's how we're going from here. So here we have, I'm trying to connect this back to here, this kind of form. You have a product of Gaussians. So here we have a product of Gaussians. I'm shortening things. And I can essentially move that product through the exponent, and it manifests as a sum inside the exponent. And that's given by this idea. Product of exponentials gives you exponential of the sum of the exponents. So when we do that, and furthermore, in this case, this is what these terms look like. This is going to be the y minus the rho of x times beta. That explains what epsilon is. That's sort of where this is going. So you're going to see this expression a lot. So if it doesn't look familiar right now, it will look very familiar soon. But anyway, this is what we have in this case. When we have this model, this function looks like this: exponential of this norm times a scaling function, which is where we get the variance, sigma squared. And then this is a scaling factor here, which ensures that when you integrate this, if we think about this as a PDF over y, when you integrate it over all those dimensions of y, it integrates to 1. So that's what this scaling factor does for us. Okay, so if you're okay for now with just accepting the fact that the likelihood has this form in this case, then you can see why it's convenient to look at the negative log. So when I take the log of this likelihood, you can see it kills the exponent. Okay, remember this. Log of, let's say, a over b is log of a minus log of b. Okay, so when we apply the log to this, we get log of a. A is exponent of this, so the log and the exponent cancel, and you're just left with this part. And then you get minus log of the denominator. But since we're optimizing over beta, we don't really care about this denominator because it has no betas in it. So this term is like a constant. Basically, we can ignore it if we're focusing on minimizing over beta. So really, what we get is we get this from the log. Then the negative cancels out this part. And furthermore, this scaling factor, that also doesn't affect the optimization. All that really matters is you want to find the beta that minimizes that norm. And that's something you've seen before. That's just our least squares beta. So the point is, when you start with this model, if you make this assumption, you say my targets equal, my noiseless, my features times my model parameters with Gaussian noise, then you find out that maximum likelihood estimation is nothing more than least squares. And this becomes, in some sense, the justification for what we did back in units 1 and 2. Someone asked, I think it was the last lecture, they said, why are we doing RSS? Why are we not doing something else, like putting a 1 norm here instead of a 2 norm? Basically, it's because 2 reasons. Number 1, quadratic, as we know, is very convenient. It allows us to actually compute this in closed form. But number 2, there's a lot of practical situations where this is a pretty good model. Basically because of the central limit theorem, which says that when you have randomness in nature, and you see a summation of many different random things, eventually that summation looks Gaussian. And so there's a lot of places in nature where Gaussian noise is a really good model. It's not always a good model, but a lot of places, good model. And that's why this is so popular. But also, this leads to a very nice least squares problem. So this is why when you do regression, this is sort of the place you always start. You just say, let's think about a linear model with Gaussian noise, which essentially means do least squares. Okay, so this is kind of bringing things back and explaining why we've been doing this RSS stuff from the beginning. It's just an example of maximum likelihood. It's not the only example. In fact, if you know that you have a model like this where you know that the noise is very non-Gaussian, that actually tells you that doing this RSS stuff, least squares, is probably a bad thing to do, and you should rethink the approach. So if you have a lot of outliers, if these epsilons are usually small, but once in a while they're gigantic, that Gaussian noise doesn't really work that way. So that would be a clue that maybe least squares is also not going to work, because it's really suited for Gaussian noise. If you give it non-Gaussian noise, it might be a very bad thing to do. So this framework helps us to bring in practical knowledge about the distribution of the noise and turn that into a different machine learning optimality criteria. So that's the key point. Next unit, we're going to talk about classification. And we're going to find that in classification, this is a terrible model. It simply doesn't work. And we're going to have to come up with a more clever model to deal with classification. And then we'll see that from that model, we just do maximum likelihood. We do everything we're doing here, but it's just a slightly different function. We go through all that steps, and it works great. So this is going to be the framework we use from now on. Okay. All right. So any questions on this, maximum likelihood for linear regression? Yes.
So in this we did not take the constant like beta 0 term once.
Yeah, good point. So all that changes if you don't standardize is this becomes an A, and then this has the beta 0 in it. So you would just get this with the A matrix. The A matrix has the column of ones. Yeah. The reason I'm doing this is because later in the lecture I'm going to connect it to the regularization, like lasso and ridge. And in that case, we don't want the beta 0 in the regularizer. So it's a little bit more convenient for this discussion to leave it out for now.
So we assume Gaussian distribution and took L2 norm. Instead of it, if we assume Laplace distribution with L1 norm.
That's right. Yes, if we would have assumed Laplace here, then this would have turned into an L1 norm, and we would have gotten a 1 down there. Exactly.
It will also match, right?
Sorry?
The results will also match, right?
The results will
Also match.
match.
Yeah.
Well, so what I'm saying is if you assume Laplacian noise here, you do maximum likelihood, you get something similar to this, but instead of the squared L2, you have L1. And that, yeah, then you can see the power of this approach. If you know something about this distribution, you can customize the loss we use to train our parameters. We'll actually see an example of this when we talk about lasso in a few more slides. Okay, good. All right, any other questions before we move on? Okay. All right, so the main thing until now to realize is that we have not put any prior belief on the beta vector. So what I mean by that is maybe you're working on some machine learning problem, and you know that for some reason you know that if your model fitting gives you like beta values that are on the order of 1 million, you know that there's something that's not right about that. Okay, so let's say you know that. Well, there's no way to incorporate that information into this formulation. It may be that if you do this, like we mentioned with a very correlated X matrix, you might actually get super large values. So how do we bring in that information? So it turns out to bring in that information, we have to do something a little different than maximum likelihood. We have to use this thing called map estimation. Okay, so that is going to allow us to bring in that prior belief on beta. So in this case, what we're saying is the belief is that beta should not be gigantically large. In other words, beta should be closer to 0 than some gigantic value. So it turns out that in this case, we're going to, instead of doing maximum likelihood, remember maximum likelihood was, let me write it. Okay, so beta maximum likelihood was arg max over beta times the probability of y given x and beta, just for reference. Now we're doing something where we've actually swapped the ordering here. We're maximizing the probability of beta given our data x and y. Here, we're maximizing these model parameters so that they best explain y and x in this way. Okay, so we've kind of moved things around. Okay, so we'll talk about that in just a moment, but one of the first things you can notice about this is if you're dealing with this quantity, probability of beta given x and y, that means you must be modeling beta as random. There's no getting around it because this is a conditional probability. So over here in maximum likelihood, we never thought about beta as a random number. It was just this fixed deterministic thing. Now we've changed completely and we're saying no, beta is actually a random number, and this is like a conditional distribution, the probability of beta given y and x. Okay. And we have a different interpretation now. We're looking for the most probable beta given the data we've collected. So it's different than what we were doing before. This likelihood and this most probable are different. But we can actually connect them if we can somehow link this to this, make them look more similar, we can understand better what's going on. So for that, we're going to use something called Bayes' rule. Bayes' rule is basically a way of flipping the conditioning. Let me write it first in an easier way. So if you have probability of A given B, and you want to flip those for some reason, you can write this as probability B given A times probability of A divided by probability of B. So in other words, maybe you just simply don't know this expression. You don't know that model, but maybe you do know these other models, so you can write it in terms of things that you do know. So that's how we're going to use it. So this is Bayes' rule in its simplest form. Now, if I put an extra conditioning variable, let's say x, everywhere, that's essentially what I'm going to do next. But really, it's just still Bayes' rule. It just happens that I'm treating x, I'm plugging in x everywhere and just thinking of it as this thing that I know. Okay, so here I have probability beta given y and x here. And then I'm swapping the order of these. So I get y given beta and x, probability beta and x, probability y given x. Okay, and now we can further simplify it a little bit. So this is our likelihood, right? So we know how to deal with that. That's exactly what we were working with on the previous page. So let's assume we know how to deal with that. We have a model for that. What about these other terms? What about this? Probability of beta given the training features x. So usually beta for us, we have in mind a model. That model takes x and some parameter betas, and it explains how y occurs. So usually the beta is not determined by the x. It kind of connects with the x to explain the target's y. So in that sense, beta does not depend on x, so we can just change this to probability of beta. In other words, beta is independent of x. So this is how we usually think of beta. And it turns out that this thing on the bottom, it doesn't really bother us, because what we want to do is we want to maximize this probability of beta given xy. We want to maximize that over beta. So I want to maximize this over beta. If I think about that as maximizing over beta, this is just some scale factor that scales everything. It doesn't affect finding the optimal beta. The beta that I'm looking for is the thing that maximizes the numerator, and the denominator just happens to scale everything. So in other words, when I do this argmax of this term, that's the same thing as argmax of the denominator. I don't need to worry about the numerator. The numerator, I don't need to worry about the denominator. So at the end of the day, maximizing this boils down to this. The map solution, Okay, so the map solution is argmax over beta times the product of two things, the likelihood, which we know from the previous page, and this new thing, which is the prior distribution. By prior, that means before we collect any data, we have a belief already about what the betas are. So the prior is our belief about beta apart from the data, and then we have this information that's all about the data that has nothing to do with our prior, so it's this nice decoupling. And when you take the product of them, actually, when you take the product of them and scale it, you get this thing, which is called the posterior. So posterior means after you collect your data, you have a new belief about the beta. Before you collect your data, you had your prior belief. Afterwards, you take in the data, and that gives you your posterior belief. And the posterior involves the likelihood and your prior and a scaling function. Okay, so overall, when we take this map approach, we're not only using our likelihood, but we're also bringing in our prior knowledge. We're looking at the product of those two things. And that is how we're going to choose the best beta. Okay, so likelihood is how well beta agrees with the data. Prior is how well beta agrees with their prior belief. So when we do map, we use both the likelihood and the prior. When we do ML, it's like we're doing this without any prior. We're just looking at this alone. From another perspective, it's like as if we had equal prior probability everywhere. So as if this belief about beta is just all betas are equally good. Now we're saying, nope, some betas are better than others. I believe in some betas more than others. So for example, if you said, I'm pretty sure that I should not get massive values for the beta coefficients, that's kind of like saying the beta should be close to zero, not far from zero. And there's many different distributions that express closeness to zero. Like the Gaussian could be 1. Gaussian with the right variance says it should be kind of, maybe kind of big, but overall centered at 0. There's many different ways to express that, so there's many different choices of that prior. Okay, so we've seen maximum likelihood, which involves no prior beliefs, and map, which involves the likelihood and the prior belief, in case that's useful to us. So over here, this is an example, least squares of maximum likelihood, where there's no prior belief about beta. But we also have seen these regularization techniques like ridge and lasso that actually we'll see are just versions of this, where they have particular prior beliefs about beta that lead to those regularization terms. So that's the next thing we'll look at. Is this overall idea about map estimation making sense? A little bit? Any questions? Okay, so we can be a little more concrete. Let's look at regularized linear regression. So we know from the previous equation that this is our map estimate. So just like we did with maximum likelihood, if I want to maximize this over beta, that's the same thing as minimizing the negative log of this over beta. So let's do that. Let's put in the negative log. And now, if I take the log of a product, that's the sum of the logs. So this gives us negative log of the first minus log of the second. And now let's take our linear Gaussian model as a way of relating fixed beta to y. Let's explain that by, well, it multiplies the features and then we have independent Gaussian noise added. So when this happens, we know that the negative log likelihood is this quadratic plus a constant. The constant comes from these terms. Okay, so this is our negative log likelihood is just this quadratic plus a constant. And then let's just plug that in for this. So here we have a quadratic, and we still have this minus log of probability of beta. And now if I'm minimizing this over beta, that's the same thing as minimizing a scaled version of this over beta. So I can actually just multiply both of these terms by 2 sigma squared. And these are going to result in finding the same betas. So if I multiply both terms by 2 sigma squared, I'm going to cancel it here, and I'm going to introduce it here. So now, the reason I'm doing this is now we see RSS exactly, and we see one other term. I'm just going to call this plus phi of beta. That is exactly what we said regularized least squares is, regularized RSS. And that was the framework that we used that eventually led to Ridge and Lasso. So we're seeing this once again. Okay, so anytime you have regularization plus RSS, you can explain it as saying, well, you must have assumed linear Gaussian likelihood, and you must have assumed some probability distribution for which you get this log and this scale factor. The scale factor is determined by how much noise you have in your targets. Okay, so this map is a way of explaining regularized linear regression. Let's be even more specific. So this is the equation from the previous page we just saw. Let's imagine that our prior belief about our betas is that the individual betas, let's say that they're Gaussian, mean 0, variance v, independent, and all distributed the same way. In this case, the probability on the vector of betas is the product of the probabilities on each of the individual beta j's, and that is just a 0 mean Gaussian with a variance of v. So this is what we get here. So now what is log of this joint distribution here? Well, if I take the log of this, then I'm going to get, this log is going to turn into a sum, and then my log is going to cancel this exponent, and this is going to end up being another minus log of this, which is a constant with respect to beta. So finally, log of probability of beta is just this quadratic plus a constant that doesn't depend on beta. So if that's the case, now you can see that I plug that in here, and I get this term. And this is exactly ridge regression with a particular value of alpha, which is usually what we call this. You can see here, you know exactly how to set alpha. It's your measurement noise variance divided by your prior variance. That tells you exactly the optimal alpha that makes these betas the most probable under that model. Okay, so this is a way of explaining ridge regression. Ridge regression is just like doing this linear Gaussian likelihood plus another Gaussian prior on your coefficients. It's just a way of saying your coefficients shouldn't be that far from 0. By selecting v, as v gets smaller, that means you believe they're closer and closer to 0. And you can see here, as v gets smaller, this scale factor increases, and you're putting more and more penalty on this, which is going to bias your betas closer to 0. It's going to pull them closer to 0. Right? And that's what we saw. We saw as alpha got bigger, the betas got closer and closer to 0. And maybe that's, if we believe they should be really close to 0, that would be the right thing to do. But you could say, well, you have to be very careful about this. This prior assumption, if you're just using it without really believing in it, you can run into some problems, right? Because that's going to be like using a very large alpha, which is going to result in tiny betas, and maybe that's not what you want. So you have to be careful in terms of how you build your prior model, because that will affect the final results you get. Okay. So there's another option. This is beta j is IID Gaussian, you get ridge regression. What if beta j is IID Laplacian? So let me just draw a little picture. So when you have Gaussian data, that means you have this bell curve. This is not a very good picture. Sorry, but you kind of know what it should look like. So when you have Laplacian data, it looks instead like this. So it's so-called heavy-tailed. These tails, the probability vanishes very quickly. It's e to a quadratic, e to the square distance from the origin. This is e to the distance, so they fall out less quickly. There's a lot more mass in these tails, and that would be like saying, compared to this model, which says that values out here should be extremely rare, this model says values out there are actually not all that rare. So that allows you these outliers. Once in a while, you get these really large values. That's what you expect. So if you make, in this case, what we're saying is, once in a while, the betas could be quite large. But you have this peak here at the origin, which says, in the end, as we know, that maybe the values, beta should often be exactly 0. Okay, so anyway, let's say we make this assumption. This is what the PDF of each of the beta j's looks like. Lambda here is going to tell us how quickly the tails fall off. If you look at the log of the prior, then, okay, the log of the product, that turns this into a sum. The log gets rid of this exponent. This turns into a constant, and you're left with the sum of those terms, and if I take the sum of the absolute values, that is just the L1 norm. Okay, so that's how we get this. So then I take this log of beta, and I plug that into here, and that gives me this regularization, which you can see is lasso, where alpha takes on that specific value. So now we have a way of interpreting lasso as Gaussian measurement noise and a prior belief that the betas should often be 0, but once in a while it can be some pretty big values, Laplacian. And that gives us lasso with a particular value for alpha. All right, any questions on this? All right, so just to summarize then, we have this new way of thinking about machine learning, statistical parameter estimation. So we build a probabilistic model, or we assume a probabilistic model that relates the targets and the features and the unknown parameters using some conditional PDF. We define maximum likelihood. That way of fitting your parameters is to maximize this likelihood or minimize the negative log likelihood. And when we do that, we bring in no prior beliefs about theta. We have another option. If we have some prior belief about theta, we can instead maximize this, maximize the probability of theta given the measured data, or equivalently minimize the negative log likelihood minus the log prior. And that does use a prior belief here. Okay, so these are the two main ways that people think about machine learning from a probabilistic sense. And at this point, it's just sort of a matter of how you build this probabilistic model and how exactly you do the optimization over theta. And so that's what we're going to focus on for the remainder of the course. Okay, so one last topic very briefly is, can we do linear regression with multiple targets? Until now, we've only focused on one target, maybe many features, but a single target y, right? Like many copies, many examples over trained data, but just one thing we're trying to predict. So now the idea is, we're actually going to predict k different things using the same features. In order to do that, we're actually going to use capital K different beta vectors. Okay, so this is a row vector here. This is our intercept, our augmentation for our intercept, and then here are all our D features. So this row vector will multiply these columns, and that will give us another row vector. And in that row vector are our k different targets. If this is sample I in our training set, this is again sample I. So we have many such samples. We have n such samples. So what we do is we stack these row vectors on top of each other, or you can look at it like this. And then we, of course, stack our features on top of each other. We end up getting a matrix of targets, a matrix of features, and a matrix of prediction coefficients. Okay, so we took our previous model and we just expanded it from vector to matrix. We'll call this, there's no capital beta, so we'll just call this B. And we'll call this capital Y instead of vector Y. Now it's a matrix, and this is the same A as we had before. Okay, so this is matrix Y is approximately equal to A times beta. So the next lab will actually involve multiple targets. So that's one of the motivations for talking about this. But this is now, we can think about it in the maximum likelihood framework. So we're saying our target matrix Y is feature matrix X times parameters beta plus this E matrix that contains noises across all the different targets and all the different data samples. So we're just going to assume that all the different elements in that E matrix, they're all independent, identically distributed, zero mean, sigma squared variance. Now, if we're going to do ridge regression, we also have Gaussian assumption that tells us that all the different B's have a particular variance, zero mean. And when we do this, we get this map problem where here we have our likelihood, and here we have our this is negative log likelihood and negative log prior. Now, one important thing to point out, just a notation thing, but it's still important, is that if you have a matrix and you want to look at the sum of all the squared values of that matrix, that's called the Frobenius norm. So here, that's what we're doing. We're looking at, because these are all IID Gaussian, we end up the negative log prior. We want to have all the values squared and summed up. We have to use the Frobenius norm to describe that. If you make a mistake and use the usual norm on matrices, and maybe you do this in coding, you just say the 2 norm, you'll actually get the wrong answer. The 2 norm of a matrix, or the usual norm of a matrix, is actually the maximum singular value in that matrix. It's very different than the sum of the squared elements of the matrix. So you just have to be careful. This is the Frobenius norm, this is the Frobenius norm, not the 2 norm. Okay, so this is ridge. Maximum likelihood, you just do this alone. And finally, lasso, you have the 1 norm on the matrix, which is the same as a 1 norm on the vector. It's just the sum of the absolute values. So that doesn't change, but Frobenius norm here. And finally, the last thing to know is scikit-learn doesn't care if the Y is a matrix or a vector. It works for both. So nothing new there. You just pack in all the targets, pack in all the features, and it will return for you, if you ask for it, all your beta as a matrix. Or it will use them for prediction. So it's very convenient. Nothing needs to change with the coding once you go from scalar to vector targets. Okay, so an important lecture, but that's it. That's it for the unit. Next time we'll launch into classification. Have a great weekend, and let me know if you have any questions after class.